In this video, we're going to talk about curve sketching in R2, and this is section 5.4 in the textbook. So before we talk about the theorem that we want to talk about, theorem 5.4.1, we are going to recall some results that we need to prove it. So the first result is theorem 8a.1.2, and it says if you have a continuous function that is defined on a closed interval AB, and it's continuous at a point C, which is on the open interval AB, and suppose you've got a real number L. Now if f of C is greater than L, then there is a delta greater than 0 such that f of x is greater than L, and f of for all x in the interval C minus delta and C plus delta. So what it's just saying is if f of C is greater than L, then there is an open interval very close to C, well that includes C, such that if we take any point in that interval, it's going to satisfy the property that f of x is greater than L. Right, so that's the first result that we are going to need. Another result is theorem A.1.4, and it says that if you've got a function defined on an in open interval containing the point A, then if f is differentiable at A, then f is continuous at A. So this is just saying differentiability implies continuity. And then we are going to look at the inverse function theorem, theorem A.1.6, and it says assume that f is defined is defined on a closed interval AB to R, and is continuous on AB on the closed interval AB, and differentiable on the open interval AB, and we know that f prime of x is greater than 0 for all x in the open interval. Then the following statements are true. The first one is f is increasing on the closed interval. So if f prime of x is greater than 0, then we know that f is increasing. And then f has an inverse, and the inverse is f, it's denoted by f to the minus 1, which is defined on the closed interval f of A, f of B, right? The images of A and B will be the 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 bounds of the interval, and then f to the minus 1, the inverse of f is differentiable on the open interval of the images of A and B, and the differential the derivative of f inverse with respect to x is equal to 1 over f prime f inverse of x, right? And this is the result that we are going to need, right? So let's look at the theorem that we want to look at. It says consider a vector function r from the closed interval AB to R2 such that R of t is equal to x of t, y of t, where t is between A and B, and assume that R prime of t is equal to x prime of t, y prime of t. So we assume that the derivative exists on the open interval AB and is continuous at a point C in the open interval AB. So if x prime is not equal to 0, then the following statements are true. Number 1, there exists a real number delta, an open interval I containing the image of C, and a function f um, from I to R, such that for every t in the neighborhood of C, um, R of t is going to be equal to xy, if and only if y is equal to f of x for some x that is in the interval I and y, a real number. And then the second point is the function f in 1 is differentiable on I, and for every x in I with x of t in the neighborhood of C, f prime of x is just going to be equal to y prime of t over x prime of t, which is equal to dy over dt over dx over dt. Right. So we are going to prove this result. So what is it saying? It's saying that if you have got an r of t given by that, and you know that the derivative of r exists on the open interval, and that the function is continuous at a point C. Now if x prime is not equal to 0, so if the derivative is not equal to 0, then you can always find this function uh, that is uh, differentiable on I, and it's equal to r of t. So you get this function y is equal to f of x, which is uh, just equal to r of t, basically. So the if and only if statement is saying that r of t is equal to xy if and only if y is equal to f of x. So you get sort of a new way of expressing r of t with a function that is differentiable, and you know the derivative to be this. Right. So we are going to look at the case where x prime is of C is greater than 0. Remember that we said x prime of C is not equal to 0, so it's either greater than 0 or less than 0. So we look at one case, and the other case will follow in exactly the same way. Right. So for proof of 1, since r prime of t exists for all t in the open interval AB, we know from theorem 5.3.2 that x prime of t also exists for all t in there, right? This is because you remember theorem 5.3.2 tells us that r prime of t is just is going to be is equal to the derivatives, or the derivatives of the component functions. So if r of t exists, it means the derivative of the component function will exist, right? So therefore x is continuous on AB, and this is coming from the theorem that we talked about, A.1.4, which said differentiability implies continuity. Now since x prime of C is greater than 0 and x prime is continuous at C, therefore by A.1.2 we know that this implies that there exists a delta such that x prime of t is going to be greater than 0 for all t in the neighborhood of C. And what does the inverse function tells us? The inverse function then tells us that x, if this happens, then x has an inverse, which we are going to say x to the minus 1. So that's the inverse function defined on I, which is the image of the image of c minus delta and c plus delta. So the interval is comprises of, so the bounds will be the image of c minus delta and c plus delta, right? So for each x in this interval, f of x is equal to y x inverse of x, right? For x in the interval I. So now consider a particular point x naught, which is in the interval, and y naught, which is a real number, such that y naught is equal to f of x naught, right? So we are trying to find this f that will well, we are trying to find this f. So we take a point x naught, we take a point x naught in I, and y naught, which is a real number, such that this happens, and we let t naught be equal to the x inverse of x naught, which is in the interval c minus delta, c plus delta. So if you look at x inverse of x naught, because x naught is in the interval, x inverse of x naught will be, so if you look at this, you can put x inverse here, and then you are left with c minus delta, c plus delta, right? So x inverse times x will be the identity function. So therefore we are left with that. Now, by the definition of an inverse function, what this means is x naught is equal to x of t. So if we map, so if we say x of t, and then here we say this is equal to x of x inverse of x naught, so we are left with, so this side we will have x of t naught, and then this side we will have x naught. So therefore x is equal to x of t naught. X naught is equal to x of t naught, right? So furthermore, if we look at y is equal to f of x naught, this is going to be equal to y of so remember how we defined f of x, right? So y of y naught is equal to f of x naught, which is equal to y of x inverse x naught, which means that this is y of x inverse x of t naught, right? So if we replace the x naught with x of t naught, which we just shown that that is true, and then that is going to be equal to y of, so if we say x inverse of x, x inverse of x t naught, then the x inverse and the x will cancel each other out, and we get the identity map, which or the identity function which maps t naught to t naught. So we get y of t naught in the end. So what this means is x naught y naught, the vector x naught y naught, is just equal to r of t naught, right? So now we consider um, the converse case, because we want to prove that we've got this function such that this happens if and only if that. So we have shown so far that if y is equal to f of x naught, then r of t is equal to xy, right? We took a particular x naught and we showed that, and we took a y naught, so we had our y is equal to f of x naught, and we showed that that is just equal to it implies that x naught y naught is equal to r prime of t naught. So now we start off on the other side. So consider x naught y naught such that x naught y naught is equal to r of t naught for some t naught on the interval that c minus delta, c plus delta. Then this means that x is equal to x of x naught, so that if we take the inverse, we know the inverse exists, right? So t naught is going to be equal to, so if we apply the inverse function, x of x naught, x inverse of x naught, and then x inverse of x t naught, and then we get on this side we get t naught, and then on that side we are left with x inverse of x naught. But y is equal to y of t naught. So what it means is, if I take y naught and I say this is equal to y of x inverse of x naught, which is, so I'm sure it's clear, right? So y naught is equal to y of t naught, but t naught is equal to x inverse of x naught. So y naught is equal to y of x inverse x, y naught is equal to y of x inverse of x naught, which is just y f of x naught. So therefore we started off with x naught, which x naught y naught equals to r prime of t naught, and we ended up with x naught equals to f of x naught, and so therefore the the converse holds, and so therefore this statement is true, right? Right, let's look at the proof of 2. Now, since x is equal to x of t is differentiable with x prime of t greater than 0 on the interval c minus delta c plus delta, and x inverse is its inverse, it follows that from theorem 8.1.6 that x inverse is differentiable on I, and the derivative of x inverse of x naught is equal to 1 over x prime of t naught. So remember what we said about theorem 8.1.6. We've got this formula, so we're just applying this this part 3 here on our proof. So we get that the derivative of that is equal to 1 over x prime of t naught, where x naught is equal to x of t naught, and t naught is on the interval c minus delta c plus delta. Now, since y prime of t exists on c minus delta c plus delta, it means that f of x can be written as y of x inverse of x, and it therefore follows from the chain rule that if I've got f of x naught, I can write it as, no, I think this is f prime of x naught. It's going to be equal to y prime of x inverse of x naught times the derivative of x inverse of x naught, and that's just equal to y prime of t naught over x prime of t naught, which then becomes that where x naught is equal to x of t naught, and t naught being on the interval that, and then this completes our proof. So if you do the routine calculation, you see that that comes out right.